welcome. Thank you all for coming. So I'm Edward, and so yeah, today we're talking about tools for uncomfortably big data. Oops. Very quickly, so I was a philosophy major once upon a time. It's been a long road. That's a whole different story, but it was at Pomona College, actually. I was in LA. I'm not presently in LA. I'm in Chicago. But yeah, so after that, I worked in, I taught English in Japan for a while. I worked in campaigns. I did a lot of other things, but eventually landed as a data scientist. Figured out I was interested in data science, taught myself a bunch of stuff, and became a data scientist at Uptake, which is a startup in Chicago. We're like 6 years old now. And we use machine learning to identify problems and assets in the industrial Internet of Things, so like semis and wind turbines and other stuff like that. And so I've worked on anomaly detection, productionalizing data science, and presently working on delivering data science models and products built on them for our fleet and federal team, for mostly truck-like things. Yeah, and I like fried egg tacos. So, why does clicking not work? Anyway. So I want to start with, first of all, you and who I'm kind of assuming my audience is. I'm sorry I don't know all of you eventually, but I'm assuming you know enough R, at least, maybe a lot of R, who knows. But you're comfortable with the basics of R. You know what lapply is and how it works, hopefully. You've done some stuff, you know the basics. And yeah, so I'm assuming that. I'm also assuming if you're here, you're probably interested in, well, tools for working with a little bit bigger data. And so maybe you've run into a bigger data set and maybe things went poorly. Maybe you like accidentally killed your computer or something. It happens. And so that's what we're here to address, is like that slightly uncomfortable size. And so as any good philosophy student, I'm gonna start by defining my terms. And so small data, for the purposes of this talk, is data you can work on your local laptop or whatever, without ever thinking about its size, right? Without any doing anything particularly weird. Like the only thing you might maybe care about is like, do you have enough data to like actually run the model you care about? And so you have enough like degrees of freedom or whatever. On the opposite end of the scale, big data, meaning data that's like too big to fit on your laptop, probably lives on a cloud somewhere or in a database. And so because of that, it probably has people assigned to like take care of it, right? So you got database administrators or like data engineers that are actually like hopefully building you tooling to work with it, depending on in what situation you end up working with that. But in between, we have uncomfortable data, and this is what I want to talk about tonight, which is data which is like small enough that like you can fit it on your computer, but like you do have to think about how you work with it. And so if you think a little more and you work a little smarter, you can save yourself a lot of time, and you can be a lot more comfortable. Which is what we're going to aim for tonight. So we're going to start with a maxim. And so you're going to hear me say this 10 million times, but like the process of working with uncomfortable data is always about subsetting to what you need, which sounds kind of obvious, but like it's the thing you just got to always keep in the back of your head. Because if you're starting with big data, you have to get down to uncomfortable data, and from there you have to get down to small data. Even if you're trying to work with a whole data set, you're probably working with it in batches. And so you're breaking it down into smaller pieces and working with each individual piece, which is what you need at that individual time. So it's always, always, always about subsetting to what you need in one way or another. And how you subset, as we'll discover, matters a little bit. And so to get us there from that first arrow here, from uncomfortable data back to small data, 3 quick strategies. So I'm going to start with basics of like, before we get into fancy tools, the basic sort of ways that we think of working with things. So the most straightforward way is just like, if you can, read it all in and then subset. So like read.csv or whatever it is, suck it all into R, and then you can like subset to the piece that you actually care about. So this is good if it'll all fit in memory. It's pretty straightforward. It's not necessarily the fastest, actually, because you do have to read it all, and you might not care about all of it, depending on how much you need to subset. Strategy 2 is to subset on read. And so this only works with some tools. And so readr, so read underscore CSV and TSV and whatever else, has a call types parameter, which you can pass. I just want to read certain columns. fread from data table has select and drop parameters. You can pass a vector of column names if you only care about certain columns. And so these are pretty simple to use, and you probably already used these functions before to read some data. And so this is a good way to like, okay, this column or this CSV has like 4,000 columns, but I only care about 10 of them. Yeah, this is fantastic for something, a situation like that. So strategy 3 is a little bit more general, but it's also way more of a pain. That you read in batches, you subset, and then you aggregate. And so batching generally, right? And so the idea here, so the nice part about this is you can do this with almost any reader function, except for like some JSON ones, if it's like not ND-JSON. And so in this case, you can use like skip and nrows or nmax, depending on what the function is, but you can usually skip some rows. So move to an offset and then read like a bunch of rows and then skip to that. And we'll look at exactly how to do this. But this is kind of annoying because it requires more setup. Like it takes quite a bit more code, and there's a lot more ways in which this can go wrong because you have to think about way more things if you're trying to read the middle of a file and not read the same thing twice and make sure you get everything, but not, yeah, don't miss anything. And so like you need to specify column names, because if you're reading a CSV, like, okay, your column names are at the top, but if you're reading rows 1 to 10, that's great. If you're reading rows 11 to 20, then you need to specify your column names. Types are a problem. I put a caution down here about like, don't put 10,000 data frames in your global environment, just make a list of data frames. There's a lot of other ways this can go wrong, but it is a powerful idiom. And so it's the idiom a lot of other tools that we're going to talk about are built upon. And so they're maybe doing it underneath, even if you're not thinking about it. So it's kind of useful to kind of be familiar with it. So let's go take a quick look then. I set up some demo code here. And so we're going to use a tidyverse a little bit here and there today. So we're going to just save some data. I'm using the NYC Flights 13 data set, which is, it's not enormous. It's barely uncomfortable, I would say. It's pretty manageable, but it's representative, I think, of bigger data sets and the ways that you can handle it. And we won't have to wait around for anything to happen, which is kind of nice. Read and then subset, pretty straightforward. So it doesn't really matter what data set or data reader you're using, what idioms you're using here. If I have like, sorry, make it all a little smaller. So 19 variables, and I only care about 7 of them, like I can subset really easily. Cool, that's easy. Subset on read, again, pretty easy. So if I'm doing this with like fread, if I only care about like these columns, cool, done, go straight there. Same thing with read underscore CSV. There's like, this calls only is really the function you're looking for here. If you're trying to do this here, you don't have to, you can like specify this in other ways if you like, but that are slightly more concise. It's just a little bit of a verbose interface. But again, it does the same thing. You end up with, notice all our data is the same size over here. The third idiom though, okay, requires a lot more setup. This is all, one iteration of this. And so let's start with it. We'll say a batch size. So this is like 336,000 rows. So we'll say a batch size of 10,000. So read 10,000 rows at a time. We're going to set up an N, which is the, I'll explain in a second. And an offset, we'll start at 0. And column names, we're going to need those, as I mentioned. And we'll initialize a list because we're going to append to that list, which, yes, is a kind of not great thing to do. But if you don't know where you're going to end, you kind of have to do it. So we're going to use a while loop, which nobody ever uses in R, but they do work. And they're nice if you don't know where you're going to end up. So we're going to say, so N is going to be the number of rows in that actually get read. And so we're going to use logging, which if you start batching is really, really useful. So message will just print a thing for you, or you can just use print or whatever. And we're going to read.csv. We'll do it all in base. Subset, and we're going to append this to the list. So the length plus 1, and then we'll only use those 7 columns. Then we'll increment, and so this is the n rows I mentioned is n. So if that should be 10,000, if there's more to the file, if it's less than that, that means you read everything. And then the offset, and so where you're going to start reading, you're going to increment by the batch size. So add that, and so if I run this, hey, nice logging. And this goes kind of slow because, well, it's there's a lot of overhead to this. And read.csv is not super fast anyway. But yeah, it's pretty quick enough. But notice I still have to aggregate. So that's the iterate, but I need to like actually combine at the end. And so the common way to do this, I have this df list, which is 34 elements, pretty big. You can use do call rbind. Be careful with this. This is the base R way of doing this. It's much better to use rbind list from data table or bind rows from dplyr. In case your types are different or your column names are different, they're just a safer way of doing it. This will just fail kind of silently, but it does work if you know your data is correct, which in this particular use case, if we just save the data, we can be reasonably confident of that. And notice that like small 3b, it's in base, it's our third idiom here, gets us the same thing. It does work. The nice part about this is this lets us do other things that we couldn't in the previous, right? So like if you're just using tooling like this, I can't subset rows, I can only subset columns, whereas in here, I can do any transformations I want on df before I append it. So like this space right here, I can put any code I like in there. And so this is a really powerful algorithm, even though it's kind of a pain to write, which is why I'm not trying to write this live, and I predid that, I wrote this all beforehand. Again, another version of this, so you don't have to do this with a while loop. You can like pre-calculate your file size. And so, yeah, sorry, I missed where it actually magic happened. But so here, so I'm gonna use a system utility to do this. So you can word count, if you've not used a bunch of bash scripting, just tells you the lines, and so that's what it's running if I actually run this. So what I'm looking for is this, which you'll notice this is the same as the number of rows here, plus the one row for the column headers. And so this scan just pulls out that first integer for me. So n lines is that number. And the offsets then, because we know what the max is, then we can just use a sequence here, and we have a nice sequence, which is just going to count up for us for how much, where we should start reading each time. And then we can use per map DFR is super nice. This is like, map is like lapply if you've not used this. DFR is combine this into a data frame and rbind it. So it uses dplyer's bind rows. It's a little bit of a heavy function, but it works really, really nicely. And because we can chuck in a function here, we can just do more logging here to tell us where we are in the process if it's a really long running thing. And then within that, we can do whatever we want. So again, we'll just keep it consistent for the time being and just select the columns we care about. But this goes straight to a data frame because of that DFR, which is nice. And read underscore CSV is a little bit faster than read.csv. So this gets us to the same place. All these are the same thing. It doesn't really matter which one you use. For the most part, right? And so like, depending on your situation, but I think it's important to know these algorithms before we start doing fancier things with them. Cool, so let's jump back to our presentation for a second and take one more detour before we dive into fancy tools. Because I think it's really, really, really important. And that is storing uncomfortable data. So like if you don't regularly create large data sets, so like normally if you find data or you collect data, but you don't collect that much data, or if you like have not ended up in this situation yet, or you have and you're not really sure if you did well, I want to think about a little bit, what are good ways of storing uncomfortable data? Because it does actually matter, because sometimes if you store your data more efficiently, it's way easier to read. And so it can be much faster to read data, and you're going to read more times than you write for the most part. And so it's even worth it to resave data sometimes if you can interact with it more efficiently. So if it takes a little bit to rewrite it, but like it's going to make each read way, way faster, it's sometimes very much worth it. Other reasons to think that about why learning to save data a little bit more efficiently is worthwhile. You might want to save big intermediate data sources. And the third reason, which I think is just the real reason here, is that nobody really wants to deal with really miserably stored big data. So like multi-gigabyte Excel files, which like with a little bit of junk in there that's going to screw it up when you try to actually read it in, or like a 281 gigabyte CSV, which like nobody has that much memory unless you've got like a ridiculous like server setup of some sort. Like that's just crazy. So like you have to batch, you have to do things. That's not compressed. That's just not fun. And so like better ways of doing this are worth it to make everybody's life a little bit easier. So let's start with CSVs then, because everybody uses CSVs. They're kind of the baseline, right? And so when are CSVs good? So first of all, if your data is small enough that you can look at it all and that visual inspection is useful. So like for an example from like my line of work, so like we save like the data that we show to our customers, like if we're showing them alerts on an asset, like we maybe maybe we have 7 alerts or something for a particular thing, and we're trying to like look at them before we send them to them or something. Yeah, CSV is perfect because like 7 rows, you can look at it all. Other times that CSVs are kind of nice. If you want to use command line tools to look at it, command line tools are really, really great at processing plain text. And so can be really useful. The third reason, if you're giving it to somebody who doesn't code, CSVs are great because like anybody can open it in Excel or Google Sheets or whatever. With fancier formats, maybe not. You actually need a little bit of tooling around it. So when CSVs are not good, and so firstly, when your data is 281 gigabytes, and that's not a random number, that's a number from a friend of mine. It's from an open source project that somebody shared this wonderful, exciting data set. And so I'm not going to name and shame because it's a wonderful data set, but it's 281 gigabytes. So like you have to download that from the internet in the first place, which is challenging. You better hope it doesn't crash in the middle. So if you want to make sure that types are maintained, and so types as in like date times, right? If you have like POSIX CT date times, passing those through CSVs gets a little tricky. If you care about how much space it takes up, so CSVs are not compressed by default anyway. And they're not optimized. And so that 281 gigs can be quite a lot smaller if you compress it properly. And then lastly, if you want to subset it without reading the whole thing, and we'll look at why that is the case in a bit. So I want to look at an alternative, which maybe I'm a partisan here, but I think it's becoming kind of a new default, not necessarily supplanting CSVs, but it's kind of the default when your data gets a little bit bigger, at least for the time being, which is Apache Parquet. And so Parquet, if you have not used it, is a serialized compressed format. So it's like RDS if you use that. And so because it's serialized, because it's compressed, it takes up way less space than plain text like CSV. It's well supported by lots of languages, unlike RDS. RDS is an R-only thing. So you can read it in R, read and write in R, Python, C++, Java, Scala, whatever. Plus lots of tools, like if people are using Spark or something, you can definitely deal with Parquet. It also maintains types, so it takes care of your date times and integers, stay integers, and you don't flip back and forth between strings and integers. If you have like things coming and going, it's going to be consistent. If you give it to somebody, it will be exactly the same on their computer as yours. And then lastly, it's optimized so individual columns can be read without scanning the whole file. So reads are really fast, and we'll see some examples of this in a minute, but it's definitely read optimized for column subsetting and row subsetting in different ways. Has a bunch of other really cool tricks up its sleeve if you really want to read into it. So like it stores a little bit of summary statistics, so like maxes and mins for each column for a subset of rows and other cool stuff, which will make it really fast to work with such that you don't need to read the whole file a lot of the time. So what do you actually need to know? So like it's a file format. You don't need to know everything about like how serialization and compression works, but the basics of how to actually use it in R. First of all, to read it, super simple. So there's a package called Arrow. You can install it from CRAN. So install.packages and then Arrow, and that's it. Read_Parquet works like pretty much every other reader function you've ever used. It has a call select, which works like the fread or read_CSV ones that we used before. So you can pass a vector of names or tidy selection if you like tidy selection. And then it also, so cool. So read Parquet, very simple, not a lot of options there. Write Parquet, a few more options, but mostly you can't go too wrong. for the most part. But if you really want to optimize, some of these might be worth playing with. Again, by and large, works the way you think it works. You pass it a data frame, you pass it a path, it saves stuff. Things that you might think about changing. So version, which defaults to 1.0 on all Arrow stuff. We'll talk more about Arrow in a bit, but 1.0, which is kind of old at this point. There is 2.0, which enables some cool stuff and has the possibility of making things faster. You can read about the difference on the Parquet website if you're interested. But 1.0 has broader support still to some extent. And so if you're worried about that, definitely 1.0 is the better way to go. If you're trying to optimize performance, 2.0 is worth looking into. Compression, so Parquet can support lots of different types of compression. You can read through the docs on that. I don't want to like do that for you. Default is Snappy. Snappy, if you've not encountered it before, I think it was written by Google. The point of Snappy is to get you to reasonably small sizes very, very fast, rather than get you to the smallest possible size and take a while longer. So it compresses, uncompresses really fast, which is a pretty good default for most of the time, honestly. So if you do want gzip or something else, there's some other cool ones if you're really into compression. You can also set compression level, which if you've ever used that in the read or save RDS or whatever, it works about the same way with, well, gzip's the same algorithm. And then the last thing that you might think about, which is a little bit different, is chunk size. So chunk size is the number of rows to put in a row group. Row groups, the way to think about row groups maybe is files within a file. And so I borrowed this diagram. Here's the source. There's a nice little post on row groups if you're interested. And so if this kind of gray box is the whole Parquet file, a row group is within that. It's a number of rows, say 10,000. And so within that, you have each column is stored separately. So it has all the values for column 1, then all the values for column 2, column 3, etc. And then you can break it into multiple row groups. And so you can have one row group, so the first 10,000 rows, the next 10,000 rows, and then like, say there's, I don't know, 500 rows after that or something. And so this is vaguely what your Parquet file will look like. In fact, it's a little bit more complicated than that, as you might expect, because I already told you about some other junk that they chuck in there. But optimizing chunk size can actually be kind of helpful if you're really trying to optimize for read. In particular, if you're saving really, really big files, if you use a little bit smaller row group, it allows for more parallelism, right? Because you can split your file, and so lots of things are already parallelized for working with Parquet files. And so it will split the file up by row group, and then it can operate on those row groups separately on different cores on your machine without you really thinking about it. And so that's one really nice side effect. Because it does that, it also reduces memory consumption if you're operating on it, that you don't have to hold the whole thing in memory at the same time. And it can also, in some cases, allow entire row groups to be skipped if you set things up right. And so if you're reading and you don't actually care about that row group, that's a very nice side effect of it. So if you're really trying to optimize, it's worth looking into. You might, by and large, the defaults will work, but these are certainly worth reading more into if you're trying to really work in this. So one more thing before we keep moving on onto some exciting tools. So when you're thinking about bigger data, you do need to think about one big file or lots of small files. And so the nice part about one big file is it allows you, it's a more familiar idiom, right? Everybody saved a single file before. And so it's a familiar idiom if the machine can handle it. And it's not necessarily just your machine, it's also like whoever else's machine is gonna end up on it, right? So if you've got a machine that can handle a 281 gigabyte CSV, well, congratulations, but not everybody's can. And so that's kind of what you need to think about, and not even just like somebody else's, but like maybe a VM or a server or something where it's like constrained by design, right? That it's only of a certain size. And so that you need to think about kind of where this is going to be handled when you're thinking about how big a file size is practical. So more smaller files are by and large less likely to blow out machines' resources, but there is some overhead to handling files in general. So like you don't want a file per like row or something, obviously. So again, if you can hit that nice happy medium, partitioning makes parallelization really easy. If you've broken your file down, you can handle separate files separately. And so you can I'm not going to go too much into like how to parallelize things in R, but there are some nice ways with like MCL apply is a very easy kind of way to do that batching algorithm that we did in parallel on your machine and handle a bunch of data really fast. And yeah, and tooling can actually make these as easy to handle as a single file. And so we will talk about that today. And that's really exciting that you can have like nicely organized data that is actually really easy to handle, even though it's broken down. But before you break it down, you do want to think about your partitioning scheme. And so like, why are you breaking down the data the way you're breaking it down? And so like, what are the natural divisions within the data set that you have? And so if you have categoricals, a lot of times that's an easy way to think about it. Of each level of your categorical variable becomes a separate file if they happen to be conveniently sized, which they may not be. So you might need to split by different variables. Time is a common one you'll see a lot as well. So in my work, we deal with lots of signals data coming off of trucks or whatever. And so if I'm getting a signal of like engine temperature, first of all, I'm going to probably break it down by the asset, right? So like if it's a different truck, it's going to be in a different file. And then within that, it's probably going to be broken down by time that you'll get a separate file for like a week or a day or a month or however long it fits, an hour, much shorter in some cases. And so you'll see subsetting by time within files quite frequently for time series data anyway. But otherwise, you need to think about like, what is the reasonable way to do it? Sometimes there's not a perfect way to do this. And so you just go by, okay, rough size, right? You do the best you can. But it is worth thinking about, especially if this is data which is going to be read many, many times. And so you do want to think about like, who's your user of this data set and like, how is it going to be read? And if that user is you, especially, like, that's what you want to optimize for. So let's do a quick demo. This I won't take too long because I know that saving data is just not as exciting, sorry, as fancy tools, but we will get there. So we're going to write this to a temp directory. I think I actually wrote it, but we'll do it again. So again, we're going to use that same flights data. And so I'm going to group it by carrier, year, and month. They're going to be the divisions we're going to use. And then I'm going to nest. So if I do this, you can kind of see how it's going to get saved. So these are going to become, well, this is going to become a directory, this is going to become a directory, this is going to become the file name. And then these data frames that are nested at the moment are each going to get saved as different files. And so that's like 185 files that we're going to save. We're going to construct a file path here. And so I'm going to put this as the month we're going to stick in. We'll pad it with 0, so it'll be all pretty with sprintf, which is not really necessary, but you know, it's pretty. So this is the file path that we're going to use. And so these are all 4 different carriers here: year, month. These are all January, but different carriers, just the way things have to be sorted at the moment. And you can see these are all not necessarily the same size because of the way I partitioned it, and that is something to think about as well. And then we're just going to use pwalk to iterate. It's like lapply, but in parallel, kind of like do call map, I guess. And so what this is doing, yeah, creating a directory if it doesn't exist. And then we're just using arrow right Parquet, which I mentioned before. So dots is going to be 1 row of this. And so we're going to save dots.data, which is the data frame, to dots.filepath, which is just this. And then we're going to set some parameters. So version, we're going to use 1.0 today. I believe Arrow Datasets will talk about works with 2.0. Drill, at least the version I'm running at the moment, does not. Chunk size, we'll set to 1,000 or 10,000 lines for kicks. I don't think you're going to see a big benefit from that, but yeah, and compression will keep it snappy. That is the default, but yeah. So if we run this, this will happen pretty quick. A little bit. Yeah, there we go. So that saved all our files for us. Let's take a look at what this actually looks like. So if we list the directories in this directory, flights directory, well, it goes down a little bit, but you can see what's there. In one of these subdirectories, so American Airlines in 2013, everything's in 2013, so those are not actually super interesting. So we have 12 files, 1 for each month. And if you not use tree is super cool. You might need to install it on your computer. But this is actually what this kind of looks like. Is a maybe easier way to think about it is we have this flights directory. I don't know who 9E is, but AA is American Airlines, year 2013, month.parquet. that's what we've got at the moment. So cool, we wrote some data. So let's get to the fun stuff. So tools for working with that data. So strategy 3 here would still work, especially because the data I'm working with is not actually crazy big. It's big, but not huge. It would work fine. But tooling can help and make this a lot easier because remember, strategy 3 is kind of a pain to write in terms of batching and making sure it all works right. And so we're going to talk about two things today. So Arrow datasets. So these two tools we're going to talk about. First of all, they're very, very non-exhaustive. There are lots of other tools around this, especially kind of things along the lines of Drill. There's Athena, there's Presto, there's lots of other things. They're all wonderful and good. Drill is just kind of convenient and there's nice tooling around it, which is why we're talking about it today, but lots of other good things. If you learn this, they will be kind of easy to learn as well. But these tools just make it easy to learn, to subset to what you need faster. And so the difference between these Arrow datasets, very, very lightweight. So it's easy to install, get running with. It's not super powerful, unfortunately. Drill is kind of the opposite. It's a little bit more work to get installed, get set up, but it's super, super powerful and can do a lot of things. And so you can query on this data like it's SQL, right? Is where we're headed here. So let's get started. So Arrow then, to take a step back. So Apache Arrow is a large project. It's focused on standardizing how data is represented in memory on a computer. So I believe it's both rectangular data, definitely, and I believe hierarchical data as well. So Wes McKinney, I believe, is the guy who's running it, as far as I know. He's the guy who created Pandas and Python. And so the idea is if you standardize it in memory, then you can use the same piece of memory for in any language. And so you don't have to copy data. And so it's super efficient. So this enables all sorts of really cool things. Arrow datasets are a tiny little piece of this very big puzzle. And so that's what we're going to focus on today. They also, as you can see, support are the kind of avenue that we get access to Parquet and R and Python as well, although there's other options there. So datasets are relatively new compared to Arrow as a whole, and definitely compared to Parquet, which is pretty stable and well established. There was a precursor in Python. It was focused only around Parquet, and so the whole idea is not terribly new, but Arrow as a whole is pretty new to R. I think the Arrow package was created within the past 2 years, but it's got solid support from our studio and well, a lot of really serious maintainers, and so there's some support behind it. It's not going anywhere. So datasets, they may change, is what I'm saying here. They're still working on them. They're under development a little bit. I would not put any of your code around them too much and assume they won't change, but they shouldn't. They're fairly stable. They'll let you know if things change. It does support a limited subset of dplyr syntax we'll look at in a moment. You can do it without dplyr, but it's honestly a lot harder to write that way. It's possible, but it's just not worth it from a mental sanity perspective. So it's great for subsetting to what you need. It's not great for calculating summary stats or sophisticated operations. And we'll look at what it can do and can't do in a moment. And so to open it or to create an Arrow dataset, it's super simple. You just Arrow and then open dataset is the function you're after. And so you pass that sources, which is a path to the directory of data files or individual file that you're trying to read. And then format is the file type. And so if the default is Parquet, but it also supports CSV, TSV, and Feather. Feather, if you're using Feather, you should just move to Parquet. They're similar, but Parquet is just better in a number of ways. But yeah, CSVs certainly are everywhere, TSVs occasionally. And some other things as well. That's not exhaustive. The other parameter here, this is all well documented, so I won't bore you with the details, but partitioning is the other parameter which is useful here. And so this you can use to capture the directory structure within the source path as variables. And so I think that's kind of confusing, but if you look at an example, it makes sense. And so if I have a path like this, right? So I have a folder called 2020, a folder called 09, 22, and then a data.parquet file in there. And so I'm going to pass this first part, the 2020, 09, 22 as sources. And if I pass partitioning and I pass column names here, so year, month, day, it will turn these three things into variables in my data set, even though they're not actually in data.parquet. So it'll extract the information from the file name and make it part of your data set. So you can actually do stuff with it, which is very, very nice because a lot of data gets stored this way. There's other ways of doing that it can be set up as well. There's like Hive style if you like that, but that is kind of unnatural to people that have not used Hive, I would suggest. The dplyr syntax that you can use with it, if you've already used dplyr before, it will all look familiar. If you have not used dplyr before, you can only use the most basic bits anyway, so it's pretty easy. So select for selecting columns, filter for selecting rows, rename for renaming things, and group by. Filter, though, you can only use with very, very simple conditions, like inequalities, basically, and a tiny bit more, but not much. And group by, I honestly can't figure out how you could use it productively. I mean, it works, but you can't, like, it has no effect. But this might get further developed in the future. It's still under development. So it has delayed evaluation. So if you use dplyr with database backends before, this will look familiar, but you use collect. So you set up your query. So I want these columns, I want these rows. To actually get the data, you pass that into collect to evaluate your data and pull it all in, which, yeah, just like a database. So it doesn't, at least yet, support mutate and summarize calls, and so it will throw an error at you and yell at you if you try that. Bottom line here, great for subsetting to what you need, not great for your whole workflow. So for that first stage of I've got a bunch of data on my disk and I just want this part of it, it's great for doing that without a lot of code finagling. So let's take a look and try it out. So we're going to use, well, we'll start with the CSV that we wrote. So it's a single CSV, the whole data set in there. And so we can specify that it's CSV, pass a path to it with arrow open data set. If we print this, it's a bit big. Let me expand this. So it prints kind of weird. It's not like a normal data frame. Excuse me, it tells us we have a single CSV in there, all of our columns, and types. These are arrow types, not R types, but you can kind of see how they'll translate that strings become character, integer, int64 becomes integer, etc., or int64. And timestamps are in here as well. And cool, if you can actually dive in, so if you do, so yeah, if I do that and just look at my completion, this is an R6 object if you've ever used R6, but there's a bunch of like parts of this, and so we can look at all the pieces of this. And so like, well, yeah, I'll do this. So files is the file, it just stores a reference to where your files are on disk. And so this is just a single one. Format is CSV. The number of columns is 19, which is correct for that file. And the number of rows, well, it doesn't know. It gives us a nice warning. And that's because to find that out, it would have to read the whole file or do something to the file, and it wants to delay that as much as it can. So, okay, so I got this again. So if I want to select those 7 columns like we did in the previous exercise, so like I do it the same way. So like with dplyr syntax, this looks pretty familiar. If I care about those, then you can figure out which ones you want pretty easily here. And if I run this, well, it doesn't actually give me any data still, right? But you'll notice that, okay, this is a lot fewer columns, so that's good. And to actually get it, then I just pipe into collect, and hey, cool, that's the 7 columns, all of the rows, and so that did the same thing. I can also filter however I want within that. Well, not however I want, but with some restrictions. So if I want to say the destination is LAX, because these are, well, origin and destination for flights that we're talking about here, I can do this, which I couldn't, again, do with the like fread selects or like the other kind of shortcuts that way. I can do row filtering here pretty easily. And so now instead of 336,000 rows, I'm dealing with 16,000 rows, which is a little bit more manageable. So that was a single file. If I want to work with a whole directory of files, it works exactly the same way. So flightsdir is the directory where we save those 185 files. This, well, looks familiar, but now when I look at the number of files in there, well, there's 185 of them, sorry. And the format is now Parquet because that's how we save them. And num calls is 18 because I subsetted some out to turn them into directories and things. Interesting bit here is num rows, it actually tells me. Because Parquet saves some metadata in there as well, it knows how many rows there are without actually reading the whole file, and so it can figure that out for us, which is quite nice. Again, this works the same way once it's here. You can also use tidy select things here, so you can like throw regex in here or whatever. I know there's an ends with one if you want, but yeah, select all the times. These are weirdly formatted times. If you ever work with this data set, this is actually 1048, no colon, but yeah, work for later. Filters, you can get, this is about as far as you can go with filters. So you can do like a value or like a variable is equal to a value, it's an inequality. You can do NAs and such. That's about it. So what you can't do then, so this does work. What you can't do is, so you can do a group by, but you can't do a filter. So if like I want to see like there's 10,000 flights, filter to groups where there's 10,000 flights for that carrier, that's not going to work because N is not supported here. And so if I try to run this, it'll just error out and say, yeah, you have to collect before you can run that, which I don't want to do because that would be the whole data set. In this case, it'd be fine, but for something bigger, it definitely wouldn't be. And I can't mutate because that's adding new columns. You can't add any new columns here, basically. It's restrictions. That'll fail. It'll tell you to collect. Summarize, same deal. It can't summarize. So that's kind of your limitation. So super good for like shrinking stuff down and just like grabbing rows and columns, which is actually really useful. And because it's so lightweight, I think this is still a great way to get started, a great tool for working with a lot of bigger data without like a huge amount of overhead. But if that's not enough, we're going to talk about Apache Drill. So Apache Drill is a power tool. And so what is Drill? Well, it takes a little more explanation. So what does Drill say it is? Well, this is their quote from their website. Boiling this down a little, highlighting for you, it's a SQL query engine for local files. That's what it boils down to. So it treats local files like they're a database, and so you can write SQL against them. And so the files can be anywhere, including your hard drive, but also, as you'll see here, like Amazon S3 or Azure Blob Storage or Google Cloud or network attached storage, or like basically anywhere. You can set it all up. Might take a little setup, but you can do it. It supports lots of file formats, not everything, but quite a lot. So CSV, TSV, Parquet, JSON, it does really well with JSON actually. It can be a bit verbose to write the SQL for it, but it's surprisingly good. Excel files, image files, all sorts of weird stuff. And then the last thing, so instead of iterating, we're going to use globbing. And so globbing, if you don't know what that is, if that just sounds like a strange word, that's like the stars you put in commands, in command line commands for bash or whatever. So like ls, if I want to see all the CSV files in a directory, in the temp directory, that's globbing. And so that's how it works instead of listing out file names and such. So the basics then. Installation is a little more complicated here. We can't just install an R package because this is not by itself an R thing. So the way to do this is a package manager by and large. So if you're on, I'm on Mac OS, and so I use Homebrew. You're on Mac OS, you probably should or do use Homebrew, I guess there's Mac ports or whatever if you want. You can just run brew install Apache Drill, and that will install Drill for you, which is nice. It does require Java 1.8. Homebrew will get that for you. If you're not on Mac OS, if you're on Linux, you have similar package managers which will work in similar ways. If you're on Windows, I've used Choco, which probably has Apache Drill. I have not checked. Or yeah, there's other ways. There's Google, or there's blog posts certainly. Yeah, so the other thing I will mention here is, so if you want to run Drill as a background service, you can use Zookeeper to do that. There's instructions here. This worked for me once upon a time. At the moment with Homebrew, at least, it's broken. And with Zookeeper that's broken, it's not drill that's broken. I think it's something's broken. But this can work if you can get Zookeeper running properly. You can run it in Docker, and that will solve all your problems as well as if you like. So that's an optional step anyway, though, as we will see. So to use R from drill, or drill from R, we're going to use the Sargent package, or sargent.caffeinated. So Sargent is ODBC and REST actually as well, and caffeinated is JDBC because it's Java. Yeah, but that does require you get RJava working, which if you've ever encountered RJava can take a little bit of work, which is why it's a separate package. But it's there if you need it. It's a little more powerful. So to start drill from the command line, after you run that brew install drill, if you're, or equivalent, whatever it is, you just run drill-embedded. And so there's other ways to start if you're not running the service. So like if you get that Zookeeper running, I'll start a little differently, but this is basically how you start it. And then that'll take you to a drill shell. And so the drill shell, from the drill shell, you can write SQL commands. And so, or SQL queries and some commands as well. And there's a web interface to it once you start it up, and we'll take a quick look at that. And from that, you can run queries, you can configure it if you want to like adjust things and administer it. If there's like a query that goes haywire and doesn't want to shut down, you can like kill it and do a lot of other stuff. So it's super cool. There's other ways to do that stuff as well if you like, but the web interface is quite nice. And it's just on localhost, and that will be whatever port you configure it with. That 8047, I believe, is just the default. Excuse me. So, how does it work then? So first, it has this idea of storage plugins. So storage plugins tell it where to look, and so the only one we're going to use today, well, it's not entirely true, but mostly tonight we're going to use DFS. I don't know exactly what that stands for, but it's your file system is FS, data file system, probably. But there's other storage plugins that you can configure. So like there's one for Amazon S3 is S3 appropriately, and there's like Kafka ones and all sorts of ones. But DFS, if you're just working on your regular file system, is what you're always going to be using. And so those are storage plugins. Within storage plugins, you have workspaces. And so workspaces are like shortcuts to paths, I think is the way to think of it. And so there's a couple default ones, and you can add your own. The default ones are root, which is the root of your drive, and then temp, which is your temp directory. But you can certainly add other ones that go to like your home directory, or like the directory where your project is, or where you store all your file or your data files, if you store them all into a certain directory or whatever. So you can configure this however you want. And so how all this fits together then is you pass this stuff to your the from clause of a SQL query. And so it's going to start with your storage plugin, and then join that by dots with the temp directory, or sorry, the workspace you're joining. So if we're using temp, and then the path you're going to wrap in backticks. And so it's going to be like from dfs.temp.backtick flights, and then you can glob or whatever in here. That's your path, and then close with a backtick. And so that's going to go in your from clause. We'll see lots of examples of this in a minute. This is the only complicated weird bit. If you have everything else here is totally standard, literally standard, ANSI standard SQL. So, well, yeah, there's a little bit of other fancy stuff, but this is the key bit. This is the other fancy stuff, but it's not necessary. It's all kind of other useful bits. So beyond just like select queries, you can also do show files from, and then that dots is like the from stuff that we just did. So you can use this like ls in your command line, or list.files in R to show what files are there and kind of navigate before you write a query. If you want to set a default workspace, you can do use and then that workspace. So like if I do use dfs.temp and then close it with a semicolon, then after that I can do from flights instead of from dfs.temp.flights. So it's just, again, a kind of shortcut thing. One last handy feature, and then we'll look at some demos, I promise. So implicit columns are kind of like the partitioning thing that we saw in Arrow datasets. And so they give you access to the path and the file name, which you can't actually do with datasets. So these are like built-in columns that you just select them and they'll just magically appear. And so FQN stands for fully qualified name, and that's the full path to that file. File path is just up to the directory, but not the file name itself. File name is just the file name, and suffix is like the file suffix, so like CSV or Parquet or whatever. And you just select them and it'll magically appear. But then also, and this is all on fairly new versions of Drill, if you're using old versions of Drill, these might not show up. But subdirectories so if you're querying a directory in like wherever your path ends here, so .flights, if I end here, so any subdirectories of flights will just show up as columns called dir0, dir1, dir2, etc. And so you can use those as well, and they'll just automatically be appended, which is really handy. And so we'll try that out in a minute. And right now. So let's go do it. So we're going to go to a shell script because everything I've been talking about is in shell scripts. And yes, I know we'll get back to R, I promise. And so first of all, the installation, I'm not going to install this because, well, yeah. So it's already installed, but you just do brew install Apache Drill, and yeah, it's Java 1.8, straightforward. To start it, we just run drill embedded. This will take a second. And then this should pop us into the drill shell. This will be very sad if it doesn't work. It's really faster than this. There we go. If you get a giant Java error when you start this up, something went wrong. That's your sign that something went wrong with your installation and you're not done yet. It happens. It's okay. By and large, using package managers to do this for you will make your life much easier because you're less likely to run that situation. But if you see giant errors before you see this, yeah, it's not going to work. If you want to see all the possible commands, you can do !help, and it will show you everything. So you can see that's kind of a lot of stuff. I will not read this all to you, but like you can see, oh, well, yeah, if you want to like, well, somewhere here is like quit if you want to exit, that will work. And there's lots of other special stuff here. Yeah, it's nice documentation. If you want to see your workspaces, you can do show schemas, and this will take a second. This is kind of slow. I don't know exactly why this is slow, but it's a little slow. So this is all your possible schemas. So DFS, these are the ones we talked about, and so I've set up a couple ones, so like repos. I have a directory called repos, and then I have some S3 ones configured as well on this computer. Cool. And so let's actually run a query, see some data. So we're going to start with the CP, which is CP is a built-in plugin, and this has this employee data set in it. And so let's just run. This is like the most basic query you can run. This is like the hello world of Drill. Cool. And this looks silly because it's too wide for the screen, unfortunately. But yeah, it does actually work. And so let's go look at it in the web interface, and it'll look a little bit better. So let's actually go copy it before I forget. All right. So this is the web interface. And you'll notice this is running on localhost. So this is only on your computer. It's not on the internet anywhere. You can network it if you really work at it. And this gives you some details of like how much memory and such it's using, because this is all separate from R, and so it's using its own resources and managing its own memory and such that can all be set up. We have these tabs up here, and so query, you can run queries, SQL probably, there's other types, but if I just post that query in there, these are SQL comments, you've not seen those. If I submit this, the nice part about this is this will give me a nice, oh, how pretty, it like doesn't go off my screen, it's all nicely formatted and such. And so you can go back and run more queries. And you can export this to CSVs or whatever. So other things here, so profiles. This is if you want to like kill things, kill long-running queries that are not going anywhere for some reason, or other things that are going wrong. You can go in here. It'll also give you some like how long things take to run. You can see that like show schemas took 5 seconds for some reason. There's some other junk in here like metrics and threads. I will not go into too much details. You can see the logs if something goes wrong. But the thing you do care about in here is the storage tab. And so this is where you can configure things. And so CP, we just ran some stuff against. DFS, we said, is the one we care about. And so if you go to, sorry, I just clicked on update here. So you can enable and disable if you have like a Kafka setup or something, you can, or Mongo or whatever, you can set things up, but update, excuse me. And so within this, it's just JSON, but it's just JSON, so you can edit it. And you can see, hey, here's our workspaces. And so there's temp, there's this repos one I've set up, and root. And so if you want to add another one, you can just like copy and paste. And so I'm just going to add another one for my like home directory. Oops. So home, and then we just put in a path here. So what's users, Visel, that should be fine. Writable, true, yeah, and that outside the workspace, yeah, probably want it to be true, say. Cool, and I just update and that'll save that. But before I do that, the other thing that's in this configuration, which is useful to know about, is this formats. And this is file formats. You'll see like PSV for pipe separated values, CSV, and so you see the type, and then extensions. And so extensions is what it handles. And CSV, you'll notice, is nothing right now because I don't want it to handle it. I want it to be handled by CSVH. It's one of the weird things that Drill does. If you have a file that ends in .csv, it assumes it doesn't have a header row, and it CSVH does. And so most of my CSVs, in fact, do have header rows. And so I move this down here. You can configure this so you don't end up in that situation, because all your types will end up messed up, obviously. And so you can mess with those as well. This is also interesting because you can see like all the file types it can handle. So like Avro files and like images and Excel. I tried Excel once, it didn't work, but you know, theoretically shape files if you do like geospatial stuff. But whenever you're done, you just hit update until you're good, and then yeah, shoot you back. So that's this. You can do a lot of stuff from this. If you like this query pane, you can certainly run things that way. But yeah, we can also just run things from the command line. You can save things in SQL files. You can do it in R Markdown is kind of nice actually if you pass connections, which will set up some connections a bit later. But let's actually run some queries on real data that we just wrote, because we wrote a bunch of data earlier. So first we saved it in that temp directory. So we're going to use dfs.temp because that's where our file is in my temp directory. And then nyc flights 13 is the first directory, and we saved a flight.csv. So that's that whole path. And we're just going to select everything from it and just read one row. And it's kind of big because, again, it's too wide for my screen. But yeah, OK. So let's read a few fewer columns. And so carrier, flight, tail num, and just get the long flights of more than 1,000 miles. And so, again, we can subset columns. We can subset rows. So this should look kind of familiar from what we worked on earlier. And this works really nicely, right? But we can do way more cool stuff as well. And that's where this gets really fun, is we can do like grouped aggregations, which we couldn't do with certainly arrow data sets. And so we can group by carrier here, and we can do count star as n, so get the number of flights by carrier, and we can sort by that number, and if we run that, there we go. And so United Airlines has the most flights out of New York City in 2013, apparently. And yeah, so we can do row subsetting as well for like distance less than 100. So super short flights, same idea. And yeah, that works. There's not very many. Delta had 2. And the navigation stuff, so show files, and let's go from this flights directory, which had more stuff in it. And so this looks like ls-l, if you've done that. This is basically the same thing, as you can see. So these are all directories. There's one directory for each airline here. And then if we dive into one of those, if we pass that back, all in backticks and temp directory still, flights, flights, some American Airlines, 2013, because it's all 2013. These are the actual Parquet files, and so you'll notice that is directory is true here and false here. So these are actual files. Cool. So let's actually do something more interesting. So let's run it on a whole directory of files. And to do that, we've got same thing, start with DFS because it's our file system, temp because we're using temp directory, and then flights directory, American Airlines, all the years, oh, there's only 2013 in there, and then all the files that end with Parquet, right? So star.parquet, all the Parquet files in there. And so if I run this, it doesn't look very exciting. It looks the same, but what it's actually doing is there's 12 Parquet files in there, and it's sucking all of them up and treating them as one big file that they all have the same schema in there. And so I don't actually need to do this fully delimited thing. If I can just like do flights/star and just get everything in there, assuming I don't have CSV and Parquet mixed or something, it'll suck it up. Or I even don't need to do that. I can just do flights and just leave it there, and it'll just grab everything in flights by default, which is probably what I want, at least in this case. So cool things. So if we want to get, so there's implicit columns I mentioned. So FQN, again, fully qualified name is your whole path, file name, suffix. And let's just do it from that flights, no / anything. And so we'll just look at the first 10 files is really what we're going to see because they're distinct files. And so these are sort of appended here, but really I'm only going to get them this time. It's going to take a second, but there we go. So you can kind of see what these actually look like in practice, right? So FQN is your full path, file name, suffix. That's that. Cool. So let's do some powerful stuff. So some stuff that we really couldn't do with any of our tools so far. And so this is the sort of stuff where even batching is not as useful necessarily, right? So because there's, so like, particularly for calculating summary stats, if you want to do those with a batching, like iterate across files or across things in that way, if you're going to calculate, say, like the mean across columns, that means you need to like do a weighted mean across like how many rows and what was the mean for those rows and like aggregate everything. And it's a lot more work than just calculating a mean by itself. But we don't have to think about that here, right? We can just do average. So this is SQL mean. And then we'll round it to 2 decimal points. And we'll save that as, or assign that as mean departure delay and arrival delay. We'll do both. And then we'll get how many flights there are. And we'll get dir0 here is our carrier. Let me just actually run, well, we'll run the whole thing. Well, let's actually just run, I'll just write it. So I can do, it also does not care about it does not care about capitalization. Sorry, I can't write and talk. So dir0, dir1 here look like 9E, that's like airline code, and dir1 is our year, that's our second subdirectory. And so these are subdirectories. The first one is carrier, and so I'm going to do dir0, we'll rename it carrier, and then our aggregations. And we're going to group by carrier and sort, but you don't have to group by carrier. And so, cool. It all, yeah, comes quite nicely. But I could rerun this with like, so group by carrier I could actually do with batching algorithms, but not grouped I couldn't without like actually doing weighting and such. But with drill, it really doesn't care. Whoops. Whoops, yeah. Yeah, actually can't in this case. But it gives me nice errors. dir0 isn't, yeah. So we need to take that out. There we go. That's the mean for everything, and notice still super fast. Yeah. So one last piece of fanciness before we leave this for a minute. So file name, we're gonna actually use that now. We ran that a minute ago for our file name here. Notice has our month in it. So if we want to extract that, we can use a SQL function called left. And then we want the left 2 characters, and which is like 04 or whatever for the month. And so we can extract that. And so we're going to group by year and month. So we're going to filter to only United Airlines here. and try to figure out what's the arrival delay, mean arrival delay for United Airlines and how many flights did they have per month. And so were they more on time in certain months than others or not? And let's run it and see what happens. And hey, it seems like, yeah, the summer was not so great in terms of delays. So like July and August were pretty bad. December was bad, but then winter didn't seem to really have an effect on them in terms of snow or whatever. So yeah, so not sure what was going on in 2019 or 2013, excuse me. To quit, I'm not going to quit now because I need it to be running later, but yeah, just run exclamation point quit, and that's drill. So at this point, probably at some point, you've asked yourself, well, yeah, you thought this was a talk about R, and so why are we talking about SQL and things? And that's because inevitably, when you start talking about big data, you end up using SQL. But you can use this from R, and so that's the next step. But I think it's really important to kind of understand what's going on behind it, because like even if you're going to write it in R, you sometimes need to think about how it's being handled behind the scenes. And so the way that we do this is with the Sargent package written by Bob Brutus. And so it defines a DBI interface and dbplier backend for drill. And so we'll look at what those mean in a minute. But it's got a lot of other really cool stuff in it as well. You can run drill just in a Docker container with drill up. So if you're on like Windows, but you do have Docker, this is maybe a nice way to do it if you can't figure out the package manager stuff. Has both ODBC and REST interfaces. ODBC is like if you've used there's a lot of DBI, ODBC sort of stuff for drill. JDBC, their drill maintains their JDBC JS Java in this case, Open Database Connector or something. JDBC, they maintain their JDBC interface a little bit better than their ODBC one. So Sargent.caffeinated is sometimes a little bit more robust if you run into problems, especially when they're related to size. You may want to try out Sargent.caffeinated, but you do have to get our Java running. So dbplier, the way this is going to work to actually pull your stuff into R if you're using the dbplier interface is, so you use this Tibble function, and you pass it either a DBI connection, so it's dbconnect and then drill, or source underscore drill, and then you pass the Tibble function that, and then what you would have passed to the from clause before, so that like dfs.temp or backslash your path goes to Tibble, and then it treats that like a table. The other really, really nice part about Sargent, which might not make sense yet, is that it has a lot of really nice helpers for SQL translation. And we'll look at those in a minute, but that's one of the reasons I really, really like this package, and yeah, why it's got me sold. dbplier basics, if you've never used dbplier before, a database backend for dbplier, which is what dbplier is. So by and large, most dbplier verbs still work. So select, filter, mutate, summarize work pretty much the same way as they ever have. Non-dbplier functions don't, right? So like tidyr functions like spread and gather are not going to work, or sorry, pivot longer, pivot wider, whatever they got renamed to, are not going to work here. Other functions, until you like bring things into memory with collect, just like arrow data sets as we saw. So when you get into mutating verbs like mutate and group by, if you try to create something, summarize, things can get a little bit more complicated. Some things are going to work. Some things are maybe not going to work. What's going to happen though is functions that it recognizes will be translated into SQL. So like mean it will recognize, sum it will recognize. Functions that it doesn't recognize, it's going to assume that you mean some SQL function and will just pass it through untranslated. So that's nice because you can use SQL functions from R, even if they're not real R functions. It's bad because, well, if you write an R function and assume it's going to get translated and it doesn't, it's going to fail. And so this takes a little bit of practice to get used to, but as you do, you'll kind of see. And the basics are pretty straightforward. So like with arrow data sets, queries are lazy. Unlike with arrow data sets, they do return the first 10 rows. So you can kind of see what your data will look like. You just don't see all of it. And again, to get everything, you run collect. To see what SQL it's going to run, you run show query. It will actually, this is a wonderful way to learn SQL if you are not very good at SQL. So let's go try it out, and I will wrap it up. I know I'm running a little long, sorry, but we're almost there. So let's load Sergeant, drill Sergeant, yeah. To make a DBI connection, so DB connect and then drill. This will look the same if you're using like Postgres or something, it'll look the same. And then we can use DB get query, we can pass it the connection, and then we can run raw SQL, same as we'd run anywhere else from the drill shell. But it'll give us a warning the first time about integers, but that's okay. But notice the big difference here is this is an actual R data frame, and I can do stuff with that after, right? So if you want to write raw SQL and you don't want to mess with dplyr, certainly can write raw SQL with DBI, and that is a totally valid way to interact with this if you like. The REST interface is a little bit different than the DBI. It's maybe a little more straightforward if you like, if you don't like DBI. So it's just drill connection, and this is going to make REST is like an API call, right? It's making to the drill. This drill's running a server. So drill query, same thing, same idea. Get a nice progress bar with this approach, which is kind of nice if it's big. In this case, it's very fast. And then the dplyr interface, so remember Tibble, this is our connection. You can either pass it a DBI connection with this db connect drill, and then this, remember, is the from part. So it's take that, stick it there as a string, and that will work. Notice it shows you, it doesn't tell you how many rows you have, it just shows you how many columns you have. It does show us though, notice our dir0, dir1 directories do show up here. Alternatively, if this kind of annoys you, you can just use source drill, src drill, whatever, and pass that to Tibble in the same way, and that also works. It's all the same, doesn't matter. Options, pick what you like, pick what you remember, I guess. It's gonna work. The SQL translation stuff, the documentation is good here. I just want to show you how to get to it. So drill custom functions, this is super nice. This shows you how things are going to get translated. So like if you try to do as.character, it's going to translate it to cast x as character, because that's how you do that in SQL. But there's lots of other stuff as well, and some special ones that have been created for this, like to date and things like that. Or kvgen is a thing if you're working with JSON, or like there's a bunch of other like special SQL, drill SQL functions, which are helpful here. But this is pretty extensive. Even more extensive is if you do this SQL translate end thing, which is the dplyr thing, I believe. This will show you all the functions you can use in drill SQL, which are with the ones that will get translated for you. And so you will see that this is really comprehensive. It doesn't give you the full details of what they do, but some are like, hey, these look like they're stringer things, which do get translated. So like, that's kind of handy because they're going to work pretty much the same way. Cool, so let's run some stuff. So if we take this Tibble, I'm going to mutate it. We saw those dir0 and dir1. I just want to rename those as carrier and year, or add those as columns, carrier and year. And then month will extract, same thing. And so we'll grab file name, which is again an implicit column, and then we'll go ahead and we'll pass this left function, which we used in SQL. We can pass it through just as is. You can do it in all caps, so you can kind of tell the difference between SQL and R functions. As integer is going to get translated to cast as int, right? But this left is going to get passed through as it is. And so this is all going to work, and I'm going to just store this as a variable, and so I'm not going to see anything. If I print this, it's still delayed. I don't actually see anything yet until I run, well, it's still delayed. I don't see all the variable values yet. And if I want to show query here, it'll show me what it's actually going to run. In this case, it's mostly pretty simple. You can see the translation here. So left as is what you think it is, and then cast as integer, and the whole thing it's renaming to month, or saving it or as a variable as month. So this case is really simple, but some of the things are going to be a little more complicated. But yeah, you can do more complicated things. If I want to count and know how many rows I have, if I want to group by carrier and count, that's going to work too, with a sort. If I want to get everything and collect at the end and actually get the whole thing, in this case, there's only 16 rows at that point, so collecting is not very expensive. And we can run complicated things as well. So let's do something actually interesting. So let's filter to destinations in LA area airports. Let's group by carrier, origin and destination, and then calculate. So these are all flights from New York. So let's figure out what's the mean arrival delay, standard deviation of it, and the max, and then how many flights there are. And this is all grouped by carrier. So we'll be able to see what flights from what origin destination on what carrier tend to be most on time or late. And so we'll see by mean arrival delay, because that's probably the one that's really going to tell us anything interesting. Cool. And it'll throw a warning the first time just about how mean treats NAs in SQL, which is fine. So, hey, so like we can see mean arrival delay. Oh, that's pretty nice. It actually arrives early most of the time on United Airlines. I think that's Newark. I don't know if I want to fly to Newark. So if I want to fly to LA or JFK to LAX, it seems like Delta in 2013 was the airline, I think. Yeah, so this is how it works. It's super powerful. You can take it super far. At some point, though, I think it's super good for subsetting and then for calculating summary stats and figuring out kind of quick queries like this. It's not necessarily worth it to figure out crazy complicated things and getting into SQL types and such, because you'll just drive yourself a little bit crazy. At some point, bring your data into R, work with it the way you're comfortable with. But definitely a powerful tool for working with these things. So I linked these, I put lots of links here. I shared the slides in the chat earlier. Lots of things here. Drill documentation is great. They have a great SQL reference if you're trying to get up to speed. Sargent, Bob Rudis wrote lots of wonderful stuff, and the websites for those are great, as well as he wrote a Git book, which I think is the best place to start for this whole process if you're trying to learn how to use drill in R. dbPlyr has great vignettes, which I very much recommend if you're trying to get up to speed with kind of how it all fits together. And then with Arrow is a big subject, it goes far beyond what we talked about tonight. In Parquet, the datasets vignette is very much worth reading. The Arrow R package is very new. It's very, very powerful. It's a little bit scary and doesn't explain everything. It's very much written for R power users, but if you're an R power user and you are curious, it can do very interesting things. Is definitely worth looking at. And that's it. So sorry, I know I went really long, but yeah, if people have questions, if people are still here.
28 people are still here, so.
I apologize for going so crazy long, but.
If you have any questions, feel free to just turn on your microphone and just ask him directly.
Yeah, I had something. Thank you, Edward, for the great talk. There's a lot of information, and that was pretty useful. I know I found that useful. So I wanted to ask in particular about some of the Arrow data sets that you were talking about. I think we talked about this a little bit in the chat, but I got the impression that these were specifically for data files where all of the columns are sort of basically fixed. Like, so for instance, you have a whole lot of data of varying sizes and different different lengths in various subdirectories, but they all have the same basic column structure. Is that
right.
correct?
Yes.
Okay.
So yeah, you do have to have kind of a fixed schema within those. Yeah, if you have like two different formats for that data or other things, it's gonna get kind of complicated pretty quickly. If you have like a bunch of files of one sort and a bunch of another, you can hack it a little bit because it has that, like, it stores the files in there. And so like you could say, okay, I know these are all stored in this format. And so I can like change that list and edit the object a little bit. But yeah, but by and large, it's built to like assume, and drill is this way to some extent as well. You can again do similar things with what you pass to that from clause, but it's assuming you have all of your data in the same format. I don't know about Arrow data sets, but drill at least is pretty good about if you have missing columns, sometimes they're okay with that at least. That it'll like if it like your second column is missing, it'll like line it up with like your third through whatever column will get lined up. But by and large, if you have like totally different schemas or something, you're gonna have problems.
Okay, thank you.
Mhm.
Hey, I had a quick question. You were showing that schema overview thing. So can you have multiple schemas in the same workspace? Or do they need to be like have completely separate workspaces for each of these kind of setups?
So let's just go pull it up. So your storage plugins, so schemas are not exactly a thing it's show schemas as the command, but like it's not exactly a thing in Drill. They have storage plugins, which is like the top level, like DFS or S3 or whatever. And then, yeah, your workspaces within this are specific to this workspace. So like if I have a temp workspace within this here, or like a root or whatever, that's only within DFS. If I have a separate one like S3, like I can have different buckets and whatever here. But that is like a similar setup within that.
And then what was that show schemas command that you showed at some point?
Yeah, that's up top. So yeah, show schemas just shows you what your workspaces are. It shows you all. So notice this is like DFS and S3 and everything. This is showing like, but it's showing you dfs.home and dfs.repos and like the whole, not just the workspace. So these are workspaces.
Okay. Yeah, so if you did have two different data sets, kind of like you were just saying, would you put them each in a different folder, call them a different workspace, and then can you do like an actual join on stuff?
Yeah, oh, totally. So like it's full SQL, so you have like the full SQL join structure works the way you think it would work. And it all gets translated from dplyr totally fine as well, which is kind of nice as well. So yeah, you can do, and that's the nice part is like they can be even like different workspaces. They can be, workspaces don't really matter. If you can even join stuff, from different sources. So if you have like some stuff in like one S3 bucket and some stuff locally, like you can actually join those and like it'll work, which is kind of cool. It's super powerful for things like that.
Cool, thanks.
Mm-hmm. Any other questions?
Any other questions?
Well, I guess there's one more I could possibly ask. I mean, just in the spirit of sort of, this kind of uncomfortable data, or I forgot exactly the phrasing that you used for it. Like, I mean, I work with a lot of data sets where I have maybe like, I mean, for instance, a series of several experiments, like in a scientific context, that are conducted over the course of a month or something, where I have maybe, 30 or 40 experiments, and each one of these could be like a single kind of workspace, like what you have there. And they have mostly the same data types, but not exactly the same kind of thing.
Yeah.
And, one thing that I have been thinking might be useful for me is a way of kind of hierarchically arranging all of these, into some sort of single object that wouldn't necessarily exist in memory, but I could kind of call together. I mean, do you know of a good way to do that, or a good sort of application for doing that?
That's a good question. So this is a problem I feel like a lot of people have thought about. I think lots of companies have kind of thought about like how to store metadata for data sets in effective ways. I don't know that there's a super clear, obvious answer. I think a lot of them are kind of particular to the situation. But I do think there was a really nice, I think naming is a big part of it, as simple as it sounds, just like naming things, because like if you're using Drill or whatever, like you can do globbing. And so if you name with a consistent prefix or suffix, or like all within a certain file structure in a consistent way, you can use globbing or whatever to always pull stuff out really easily. And so I know Jenny Bryan wrote a bunch of nice stuff on naming things back in the day, which there's some classic PowerPoint somewhere on the slide, somewhere on the internet. And then Emily, what's Emily's last name? Reader wrote a nice thing on naming columns maybe a couple weeks ago, which was kind of like similar ideas of systematizing.
Sure.
And like, I think that's the key, is like systematizing column names and then systematizing your data sets as much as you can. The other thing, and this goes well beyond the scope of kind of what we're talking about tonight, but like, I think pulling in some of the ideas from database management can be handy for this as well. And so like the idea of denormalization. And so you like, sometimes you have like extra information, but it's always like in certain categories. And so you can store those extra categories in a separate table, which you can join in if you need, and you just store a key if that key is filled in. So maybe it's NA most of the time, and that's fine. And so if you have like kind of data that you need to attach sometimes, that's a nice kind of condensed way to store it.
Okay. Yeah.
But yeah, like there's some other ideas like that, but like, yeah, it does depend so much on the situation. Like I don't have a great generalized answer. Sorry.
Right. Well, I liked your, I mean, the command to, you know, if you have a bunch of things in subdirectories, to sort of, you know, wrap that all up into a hierarchy. It's an example of that. So, yeah.
Hey, Edward, really great talk, and thank you very much, and excellent examples, etc. So just want to say thank you. And a quick follow-on question as well, and that is, are these tools that you use every day, or are some of the tools that you use every day slightly different? I just was curious.
It's a good question. I don't use these tools every day. I do use these tools now and then, I would say. Frankly, a lot of the data I work with is just not big enough that I need it. Plus, at my company, we've got like some of our architectures in Python. So like, we've already written things in Python and like Dask or other tools to like handle kind of similar problems in different ways. And so I don't do it all the time. I do find myself breaking out Drill in particular a lot when I get, when I'm doing EDA on really big data sets, which I don't do all the time, but I do sometimes. And so like if we get a new customer and we've got like a year's worth of historical data from them, which is like gigabytes worth of data, Drill is really handy for like just diving in and like pulling out or kind of getting a sense of what's where and like what's normal, and breaking things down. If you need to chop things apart or like subset, it's really helpful for rearranging that way too. So for like the kind of, it's my tool for like light data engineering, I would say. And I'm definitely not a data engineer, but I feel like if you're a data scientist, sooner or later you end up doing a little data engineering, and that's how I use it. So not every day, but definitely, I don't know, a few times a month probably.
And how about the Parquet? Do you use that more often across platform?
The Parquet I use a lot. Honestly, what I use it for the most is just like transferring data between Python and R. It's great for that because like and Pandas just has like a toParquet method to save Parquet and like reads Parquet just as easily. And so like, and you don't have to worry about like your timestamps, like parsing and all that mess. It just goes, you get exactly the same data in R and Python. Is really, really nice just for that. Yeah. And long-term storage as well. It's like a pretty stable format and compact. So yeah, there's a lot of Parquet files on my computer right now. Yes. And
then one last completely random off-topic question. That is, in your work with trucks, etc., where you're capturing kind of, if I think of the truck being the edge and you're capturing that kind of telemetry, are you using open source tools for that, or are you using a particular cloud platform, or are you using, you know, Azure Edge, or are you using, I mean, like, I'm just curious about the mechanics.
No, that's a great question. So we work mostly on the analytics side, and so we are not so we work with telematics service providers or OEMs. So they actually own the edge devices on the truck, and so they handle like how it all gets transmitted through cell networks. And so we get our data from them. So sometimes the OEMs and the truck manufacturers or the truck manufacturers and the telematics service providers are the same people in some cases. Sometimes they're not. But yeah, don't do a lot of stuff on edge, at least for trucks. My company has done stuff on edge for other cases, but not for trucks. But yeah, truck telematics is pretty well established. We've been collecting data off of it's like heavy trucks for a long time at this point. Yeah, we're just kind of in the next, actually how to use that data once you got it is where we're focused.
Awesome. Hey, thank you very much.
Yeah, thank you.
Any more questions? Or just want to say hi? Adam gave a talk last month for us, and he's here again. Yeah.
Yeah, hey everybody. Thanks, Edward. This was awesome.
Yeah, awesome. Good to see you or hear you.
This was great. Thank you.
Thank you. Thank you everybody for coming. Thank you, Amy, for setting this up and organizing everything. Organizers are great. Thank you, organizers.
Yeah, we have a whole crew.
Nice.
Yeah, I guess that's it.